Now we begin to introduce the first tier of our cleaning process. The first one is to introduce the clean room. Okay. Then clean room is the artificial space that we use to fabricate our wafers. So in that rooms, we have to maintain a very clean and particle-free. And here we show you some sources of particles. Okay, either from your air, okay, or water, and also your machinery that you have during your process. Those equipment, then you have some machine that will produce due to those frictions, metals, and they'll generate some particles. And also the people, all the people you get into the clean room, you do all the process, then those organic particles from our skin, right, our hair. And that's the main source of the particles in the clean room. And also the supplies, like paper, you have clean room papers, those chemicals, metals you bring into the room for use. And during the process, and also some browning motions, okay, and gravitational sedimentations. Okay, those are inevitable particles sources. Then, for people to get into the room, they have to be well trained and have to get the access. And also, we have to use this finger roll machine to get into this clean room. And we have to wear body suits and gloves and go through the air showers, and we have to use a mask to cover our face and hair, and we have to use the glove box and rubber gloves. Air handling is also very important. We have to maintain positive air pressures because we don't want outside with those dirt particles here will flow into the clean room. So inside the clean room, we need to get that positive air pressure. So once you open the door, it's clean air going out, but not dirty air coming. Okay, and so we have to use some filters. We call it HEPA, high efficiency particulate air filters, and to maintain this airflow. Those HEPA can efficiently filter out some particle less than 1 micrometer. Okay, so in the last lecture, we also talked about there are different class levels. Like class 1 is the most cleanest environment. Usually, when you do the lithography, then that has to maintain the let's say close 1. And here is just the particle size. We use 0.5 micron diameter as the particle size to describe that. And so again, class 1 or class 10, this number means the particle greater than 0.1 micron per cubic foot that you can find in this environment. Now, how many particles you can find? So we want this number as small as possible. Okay, and here just the pictures that you show people working in the clean room. Okay, you have people wear these body suits and wear gloves, and we have HEPA filters. Okay, so that's very straightforward. And then the second part, we talk about the wafer cleaning process. Is you use some way, either like solution-based. Typically, we call it RCA cleaning process because it's invented by RCA, this institution. Okay. So this front-end wafer cleaning based on this RCA process. So RCA means the Radio Corporation of America. Okay, that's this organization, and they involve 3 ways. The first one is to remove organic. Okay, and then second one to remove the oxide, and the third part is to remove some iron. So organic, oxide, and iron. Okay, so the first step we call it SC1. SC stands for standard clean. So it's performed in ammonia and peroxide and water. And this mixture of solution by the ratio of 1, 1, and 5 at 7 to 8 degrees C for 10 minutes. Okay, so this treatment can oxidize this organic film. Okay, and those complex group 1B, 2B metals, those metals. And because you have this H2O2, this peroxide will oxidize, and then they will grow. Okay, this organic can dissolve and regrows a very thin native oxide on the silicon. Okay, and then the next step we can dip into this buffer HF solution, right, with the HF with H2O at room temperature. Okay, so things in the first step you already grow this oxide, and the second step you dip into this HF, buffer HF. They will remove this thin oxide layer and also some fraction of this ionic contaminants. Okay, then you rinse in the DI water. DI is deionized water, which means it's like a pure, very pure water. And then the next step we call it SC2. It's performed in the HCl and peroxide solution. Okay, also at high temperature for 10 minutes. And because you have this HCl, this chlorine ion can help you to remove this alkaline ion and this these metals. And also from the previous this ammonia solution that they cannot dissolve in that ammonia hydroxide solution, you can use SC2, this step to remove it. Okay, so we can completely remove these metal contaminants, and then you rinse in the DI water again. Okay, so here just the block diagrams. First you use sulfuric. This can be used to remove your photoresist, and you can strip some oxide and rinse in the DI water. And then you go into this RCA process. We use ammonia first to remove organics, metal, and some particles, and rinse in the DI water, and then use HCl to remove oxide. Okay. And sometimes you will use ultrasonic to help you, because this agitation can help you to dislodge these particles. Okay. But you have to be careful. This ultrasonic, sometimes you break your wafers. But silicon is more robust. For some compound wafers, then you have to be very careful. Okay. And we just mentioned this deionized water. So we try to remove the iron from the waters to reduce the conductivity. So here just a quick calculation of this resistivity of DI waters. You will remove all these ions. Okay, so now we have these two ions, and this is the concentration And here are the diffusivity of these two ions and also the mobilities. Okay, so you can calculate the resistivities 80.5 mega ohm centimeter. Okay, so this is very high resistivity. So, which means that your water, your DI water has very few ions, because this ion will sometimes react with your silicon wafers, or also change some chemical properties. So all the waters here we used, we have to use DI water. Otherwise, you will increase more ions, then that will change your this chemical reaction. Okay, then this is the distilled water. Okay, typically you can compare the resistivity. Okay, in the distilled water, the resistivity is much smaller. Okay. Okay, now we move to the third part. Okay, in the previous two ways that we control the impurities, I think it's all very straightforward. But for this scattering process, I think we have to spend more time on this. Okay. And this scattering process that will help to remove those particles or elements away from the surface, which we build our transistor on the surface channel. We can move away from those particles from channel into a more deep side in your material. Okay. Okay, so then our transistor, okay, these active devices, they are typically near the surface, right? And we try to remove some metals or those alkali ions, which are very mobile, so we have to move it away from your surface. And so there are two ways to get those defects, those ions. One, you can do it from the surface side, from the front side, which we can use some dielectric layers to help us to capture those ions. Okay, so we can use some dielectric layers on the top side, and PSG, which is glass that you dop with some phosphorus and use some silicon nitride, and that will help you to capture those unwanted ions. But sometimes this dielectric field will, because the dipoles inside is filled, it is fused, so that will affect the electrical field, and that will result in like your threshold voltage change. Okay, and also for the PSG, this kind of glass that will absorb water vapor, and if you have aluminum metal inside, that will cause compression to happen. Okay, so for the metal ions, we generally use some traps on the wafer backside or in the inside this bulk wafer. On the backside, we call it this extrinsic, and inside the wafer, we call it intrinsic scattering. Okay, so this is the one that we try to remove or prevent it from contaminating our transistors. Okay, and here are some deep level impurities we also try to avoid in the silicon. Here. And here are the shallow septal or donor in the silicon. Okay, then we're going to use this figure to describe the step that we gather those unwanted metal or ions. Okay, here the PSG layer on top is this pink layer that sometimes we can use it to get to those alkaline ions, but we have to remember that it will absorb some water vapor and cause aluminum corrosion later on. And also, this is a device that we process or fabricate in this surface region. And this is the lutein zone or epi layer that we cross epi on the substrate. And here is just on the bottom is the substrate. And there are two ways of to capture the ion. The first one is to use the intrinsic gathering region. Okay, sometimes it's SiO2 that we just mentioned in the previous lecture, and also there's a backside gathering region that we can create some defects on the backside that can also help us to get us. Because as I mentioned, that those point defects, they are tend to get together and grow with each other, some like people, right? Also people will, that you have the same taste, then you will get together. So we try to create this kind of defect here, so we can make this ion to go to this region. Okay, so there are 3 steps. The first one is to free the elements from the current side and making them moving. So if you have defects, you have those ions, you want to free them first so they can move around. And then the second step is to diffuse through this silicon to the desired site. This desired site means this PSG layer or this intrinsic or extrinsic region. So we'll try to make them to move to this region, some region that we created on purpose or not on purpose. And also, then once they get into that region or that size, they can be trapped in that size. Okay. So, 2 kinds of ion. The first one is the alkaline ion, so then we'll go to your didention layer on top. And some heavy metal ion that can be trapped on the backside or in the wafer. Okay. Okay. And this figure is also very important because you can see for those point defect, especially those interstitial defect, their mobility or their diffusivity actually is quite higher than some dopant inside your silicon material. Okay. So we can see there's a region for this I interstitial diffusers to move around in your material. It's even larger than like this conventional dopant inside your silicon. And here are some like deep level metals, and also this is a silicon interstitial defect. They all move faster than your dopant. Okay. And those, because this defect, the size is different, sometimes it's larger, sometimes smaller, and they don't really fit in your lattice site. So they just move in between your lattice site so they can move faster. But this dopant, like the boron or arsenic, when they diffuse, okay, they tend to diffuse in a substitutional way, right? They will substitute another silicon and like switch the position, and then it continue to move. So that will takes more time to break the bond and to form the bond and replace the original site, and then go on. Okay? So you can imagine that kind of process will be slower. That's for the dopant. But for those defects, they can just move around quickly. Okay. So in these 3 steps, the first one to free the element, right? And the second, we'll try to make them to diffuse to the desired size. Okay, so the desired size, which means the traps, right? We create the traps for those defects they can go there and they can precipitate there, they can get together and grow, as long as they don't stay close to our surface channel. So those desired size or the traps, one is created by silicon dioxide, as I just mentioned during those CC growth process. Inevitably we have to incorporate this oxygen, and at high temperature they will form silicon dioxide inside the material. And this oxide, right? Remember we have seen these figures, right? So we have this silicon dioxide to begin to from a very small from the nucleation and begin to precipitate and to grow bigger and bigger. So we will create these traps on purpose. Right? Things we cannot get away all the oxygen. Why don't we just use it? Okay. So you can see here just the figures we have is the temperature versus the time. So we will increase the temperature quickly to over 1,000 degrees. So those oxygen begin to out-diffuse. And then and once they become mobile and out-diffusion, then we can reduce the temperature. So in this case, we try to form very small traps. Okay, we call it a nucleation. This is a nucleation time. When we create an embryo, then we begin to grow. So this size, 1 to 3 microns, and we have these concentration numbers. So once they form that very small silicon dioxide, then we can increase the temperature again. Then they begin to grow. Right? That's following this process. You have more oxygens come in, and you have some vacancy to come in, and begin to precipitate, and it grows to 50 to 100 nanometer size, this silicon dioxide. And from these SEM pictures, you can see this is some white dots, especially here. You can see some white dot, right? But not from the surface. Okay, so these white dots, they locate in the bulk of your wafers. Those are the SiO2 traps that we try to create this for intrinsic gating process. Okay, and we can do some experiment. Either we change the out diffusion time. We change the precipitation time from 8 to 48 hours. And also this is the pre-anneal time, okay, different time. So in this direction, we increase we can see that once we increase the precipitation time, like here, we can see this size of this trap begin to grow larger and larger. So if you see from left to right, at each row, you can see the size begin to grow, right? And if you change this nucleation time, so that would we can follow this direction in the y-axis direction from 6 to 24 hours. Then we can see the density to grow. Right? Those nucleation size and the density begin to grow. If we increase this pre-annealing time at low temperature. Right, so this one you see very there's the largest and most defect and will create the most efficient scattering process. And again, you have to see that, like from here, I think this figure is more obvious. Here is the clean region, right? Because those defects are inside the bulk region of your silicon wafers. But on top of the surface, it's very clean, right? Okay, so now we move to the second part of the lecture is to describe some measurement methods that we can use those methods to measure what we just described, those phenomena. How can we observe this? Like, how can we observe the defect of the particles? Okay. Okay, so for the clean room, okay, those particles, we can just use some microscope or use some optical way to maybe to scan, to see like scatter. If you have some particle on top of your wafers, then they will scatter the light. You can observe it and you can identify the quality of your starting wafers. That's for the unpatterned wafers, those blank wafers. But you have some, if you already have some patterns on top of your wafers, then we can have a good reference die or wafers to help you to compare. You can use these optical systems. Okay, so that's why in TSMC they need some people to know to do like this signal process, because you have to. There's a lot of data, and you have to. Now they use AI to train it, to make it compare this, and to identify if there's something wrong or off the spec. Okay, and also can use SEM to zoom in to identify the location of the defect. And we can also design some test structures, some process control monitors. So in this process, so we can use that to check if we have some particles inside. We can test these structures electrically. So if there's a particle, for example, maybe the film breakdown will happen earlier. For ID, you can see more leakage current of these test structures. Okay, so here are some test structures for you. For example, here just the metal lines, very strong, very long metal lines, and in between, if you have a defect that will create maybe short or open, so you measure the pad, the current between them is become short or like very low resistive current, or you can either it's open, which give you very large resistance. And also you can create a test structure like a MOSFET. This capacitor structure, if you have defect in between in your dielectric field, then that will create some charge, some trap charge inside, then you will change your demonstration voltage. And also, they will cause you to break down earlier. So you can measure this IV or CV curve, and you can get to know the quality of this film. And here are some approaches that can help us to monitor how good is your wafer surface quality. Okay. We can divide it into like three different ways. The first one is we can the incident wave. The incident beam is electrical beam. Okay, and the second one is the incident is the X-ray beam, and the third one is the ion beam. Okay, for if you inject this electron beam on the surface of your silicon wafers, either you excite another electron off your surface, that we call it AES, is OJ electrons spectroscopy. Then, or you can generate light because you give it the energy to your electron and excite it, and once they recombine, they will emit X-ray. So you will get some photon spectroscopy. You call it XES or EMP. Okay, and the second one is you can shine the X-ray. You get a lighting. Okay, and that will provide energy. Then you have some photoelectron to come out, and we call it XPS. Okay, they will have different spectroscopy, and at the different peaks, different wavelengths, or different location, then you can identify what kind of like atom-to-atom bonding, or what kind of material inside your material, what kind of elements. Or you can have this XRF, then brings X-ray in and X-ray out. Okay, and the third category that we can have incident ion beam. So we have 8 ion to bombard your surface. Then either you have some residual backscattering, okay, or you can create other ion. You impact in this surface, and you get ions come out. So this secondary ion, we can count them, we can monitor them, then we can know what's the percentage of the ions in this material. This spectroscopy we call it SIMS. Okay, secondary ion mass spectroscopy. Okay. So here, let me introduce you in details. Okay, so the first one is we use if we have like electron beam emission, right, is either the secondary electron the same as we observe in our SEM, or you have some higher energy, that's the OJ electrons, or even higher energy, that's backscattering electrons. Okay, so either is in elastic collision or is elastic collision of the incoming electrons. Okay, so that's from the energy level that there are different types of electrons you can observe. And okay, so if we have a primary electron injected in your material, like for example here, you excite another secondary electron, and which causes you some higher energy level electrons to come down and view this site. And once they release, they recombine with this hole, they release energy. Those energy will provide another electron at higher level, maybe this EL2 level, to come out. Okay, so this 1, 2, 3 process. Then we observe this ejected OJ electrons. So that's we call it AES. Okay. And again, so here, this is a valence band and this is conduction band. And here, what we talk about is the core electron energy levels here. Okay, so if this primary electrons, they hit and they can kick out these secondary electrons, and there's another possibility for this electron to come up and release energy with photon, with X-ray. So either it doesn't involve photon, then that will be the OJ process. But if we involve photon, then we can observe this XPS. This is we call it X-ray photoelectron spectroscopy, XPS. Okay. Okay. So let's go back to this slide again. If your primary beam is electrons, they will give you a good lateral resolution because electrons are easy to focus. And if you detect the beam is electron, then it will give you a good depth resolution and surface sensitivity, which is the XES or XPS. But if you detect X-ray, then they give you poor depth resolution and poor surface sensitivities. But if you detect ion like RBS or SIMS, okay, that will give you like very excellent and accurate mass element inside your material. But it's destructive, okay, because you imagine that you just impact this ion into your material that will, and once it hit this, you bombard this surface, and like it's kind of like a drill a hole into the material. And those spotted out ion, you just collect it and detect it. It can give you like a good, like the concentration profile or the elements profile with your depth, right? But it's destructive because you just damage this material. And this RBS is, I think we learned that in modern physics. Okay, so that's the material analysis that we can do to identify the quality of our surface. And also we can just directly make a device. For example, we can make this DRAM device. We can measure the refresh time. We can infer that what's the quality of your material or your dielectrical field. Or we can measure the capacitor breakdown. Or we can make a transistor. You can see the beta, like this NPN transistor, the current gain will be affected if you have some defects inside. For this diode curve, we can check if there's any leakage in this inside your junction. Okay, so that's the device level that we can make. Okay, and here we show you another measurement. It's called the photoconductive decay measurement. generally we shine a light inside your samples. Okay, and we can use meters to measure the current across this material. Because you shine the light, then you will generate a lot of electron hole pairs. Okay, so once they recombine, okay, they will provide this photon current. But if you have a lot of defects, your recombination lifetime will be shorter. So you can see the current change with your time is faster, so you can fit this time constant that will give you this recombination rate of your defect. Okay, so basically from the oscilloscope, you can see the current change with time or your photoconductivity changing with your time. And those, you have excess carrier, then they will recombine. So with this time tau r constants. So we can fit this curve with an exponential curve. So we can get this recombination lifetime. Okay. Or we can measure the capacitance. Okay, CV curve. For example, this is the curve that at time 0 we apply the positive VG on the top gate. Okay. So that will begin to repel and make those holes to move away from your interface. And also they can draw some minority carrier like electrons close to your this interface on the other side of your capacitors. Okay, so that's the typical capacitor with carriers accumulated on the other side that we can observe from this measurement. Okay, so here this is you apply VG, then you have a QG on the one side of your capacitor. Then you repel those holes. Okay, so you create a depletion region. So this QG and QD will be the same. Right? So this is a depletion layer here. And as time you continue to apply this voltage, then you will attract some electrons which are the minority carriers inside your p-type silicon, and you can form this inversion channel, this Qi. So now the Qg equals to Qi plus Qd. Once you have Qi, your depletion layer will become smaller. Okay, so this Qd is smaller here. Okay, so we can measure this capacitor as a function of your time, right? So in the beginning, it's like this is your capacitors. Now capacitance number. Okay, so once you have electrons that minority carriers, then you generate this minority carrier with a certain generation time, or the minority carrier time, and together with your surface recombination velocity. So we can form this inversion layer. Okay, so once you form this inversion layer, then capacitor will change and become this minimum. Okay, so this time will be the time that you need to generate those minority carrier from your p-type from the p-type silicon. Okay, so basically you can observe the time that you form this inversion layer. So that will relate it to your generation tau g here. Okay. And also you can, this is called Zerber's plot. You can plot the derivatives here with your C inversion over C minus 1. Okay, so this is Y, this is your X. So you plot these figures, and this is the slope, this is the intercept. So from this slope, you ready to your effective generation time. Okay, so you can plot this Zerber's plot from your CV. Okay. Okay, this is another lifetime measurement. We call it open circuit voltage decay. When you apply your voltage to a diode, then at time 0, you just open the switch, and you the charge in the beginning you force the magnetic current, but you have the diffusion capacitance, depletion capacitance inside this diode, okay, which related to some minority carrier process inside this diode. So once you open this, the voltage begin to decay. Okay, it's due to those recombination of your excess carriers. So this decay voltage with your time, okay, is like log. If you plot this, then again you have a recombination lifetime here. Then once you can plot this, you can take some derivatives and take some these parameters inside. It can help you to get this number. Okay, so also some DLTS, deep level transient spectroscopy. Okay, this can help you to identify the trap and concentration at the same time. Okay. So, but we won't get into the detail of this. Okay. Now, I think we can take a 5 minutes break and come back. We'll go to the third part about the modeling part.